Yeah, so it's very nice to speak at this online seminar. So as I said, as it says in the title, this talk is about the three-dimensional Lyoness map, which I'll explain what it is in a minute. And this is related to, or you can use this to understand mirror symmetry for this particular Fano threefold, but also some others. So let me just launch into the talk, I guess. So what is the Lyoness map? Well, it's a birational map of d-dimensional complex affine space, and it's given by this formula here. So what this map does is it shuffles all of the coordinates to the left by 1, and then it replaces the last coordinate by this expression at the end here, which is 1 plus the sum of all the other variables divided by the first variable. So this map has been studied in by people interested in integrable systems because, as we'll see later, it's an example of an integrable system. So I can think about this as a birational map of affine space, but also there's this associated recurrence relation where, so if I iterate this map many times, either forwards by taking positive powers or backwards by taking negative powers, then I can define a sequence of rational functions where I think of the essentially these are what appear as the entries in the powers or iterates of this map. So a sequence of rational functions here, xi, so x1 up to xd are just what you think they are. They're just the variables x1 up to xd. And then for I bigger than d plus 1, or I less than or equal to 0, I can calculate what it is in terms of the first d variables by using this recurrence relation, either to go backwards or forwards. And so this defines a recurrence relation in d variables, which I'll call the d-dimensional Lyoness recurrence. And so this this recurrence relation in 2 dimensions is very famously known to be 5 periodic. So when d is equal to 2, so that's I've got 2 variables, and x3 here is just going to be 1 plus x2 divided by x1. So that's clear how to write that in terms of x1 and x2. And then x4 is going to be 1 plus x3 divided by x2. And if I substitute in what I know x3 is, then it simplifies to this expression. And it looks like it's going to get worse and worse, but when I do this iteration one more time, I find that x5 is actually simpler than x4. And if I do it again, then I find that x6 is actually back to where I started, x1. So this recurrence relation is very special in dimension 2. It's 5 periodic. And this also carries on in dimension 3 too. So in dimension 3, this recurrence relation is 8 periodic. So this recurrence relation is, I mean, the terms here are a lot more complicated, but as you can see, we start with x1, x2, x3, and then x4 is 1 plus x2 plus x3 divided by x1, and x5 is going to be 1 plus x3 plus x4 divided by x1. And so these things get more complicated until you get to x6, and then start to get simpler from x7 and x8 until eventually we find that there's an 8 periodicity in this recurrence relation. So it's very nice and kind of completely unexpected behavior. And another very nice and completely unexpected behavior is that both these sequences have what's called a Laurent phenomenon. So you notice that when I calculate the next term in this sequence, for instance, if I've got to x6 in the dimension 3 recurrence and I need to calculate x7, then I have to do 1 plus x5, 4 plus x5, and then I divide by x6. But x6 has a very big and non-trivial numerator. So the fact that this numerator divides 1 plus x4 plus x5 exactly is somewhat surprising. So when I say Laurent phenomena, I mean that all of the terms that appear in these recurrence relations are Laurent polynomials. So they are of the form polynomial divided by monomial. And so you might think that this is going to go on forever, but unfortunately it doesn't. It breaks in the very next dimension, dimension 4. So when in these two cases that are on the previous slide, dimension 2 and 3, this is an example of an integrable system. So all I know about integrable systems is what's written on this slide. So basically, this recurrence relation, you can ask for invariant functions. So functions that are functions in x1 up to xd, which when you apply the Lyoness map to them, don't change. And the maximum number of non-trivial invariant functions that a map like this can have is the dimension -1. So these are known as first integrals to people that study these things. And when d is less than or equal to 3, this map has this many invariant functions. So for example, I could just sum x1 up to x5, and that would be fixed by the d equals 2 map. And in dimension bigger than or equal to 4, as I said, the recurrence relation, so A, it's no longer periodic. So the nice periodicity that we had in dimension 2 and 3 doesn't exist anymore. And also, the Laurent phenomenon doesn't exist either. So when d is bigger than 4, you'll find that the functions, the terms in the sequence start to have denominators which are no longer just monomial. And the corresponding integrable system is well, it's not an integrable system anymore. So it doesn't preserve the full number of invariant functions. However, it is known to still have quite a few. So it has roughly dimension divided by 2. And it turns out that these are all Laurent polynomials, and they're fixed by this map. So these Laurent polynomials, as we'll see towards the end of the talk, are in the dimension 2 and 3 case are interesting in terms of mirror symmetry, but I don't know in dimension 4. There are a family of Laurent polynomials that are fixed by the Lyoness map in dimension 4, but I have no idea if they're actually interesting to people that study mirror symmetry or not. But let me just start by way of introduction with a recap of the dimension 2 case. So in dimension 2, there's some very beautiful geometry that underlies this very simple recurrence relation, periodic recurrence relation. And so I just want to explain briefly the dimension 2 case, and then try and generalize some of the features of this to dimension 3 and show you how it generalizes. So this talk is hopefully just supposed to be a bit of fun, because I think this is a very pretty story, and hopefully you agree. So if you recall from the previous slide, in dimension 2, this Lyoness recurrence is 5 periodic, and it generates these 5 rational functions. And so it's very well known that actually these five terms, we can think of them as coordinates on an affine del Pezzo surface. And so what do? Well, basically I just take the surface, which is defined by the vanishing of all of the ideal of equations that hold between these 5 terms. So that ideal is actually just generated by the 5 equations that say x1 times x3 is x2 plus 1, x2 times x4 is x3 plus 1, x3 times x5 is x4 plus 1, x4 times x1 is x5 plus 1, and x5 times x2 is x3 plus 1. So very concretely, it's just an affine surface in 5-dimensional space, given by these 5 equations. And I have an affine surface. I can take the projective closure of that, and this turns out to be a projective del Pezzo surface of degree 5, a dp5. And the bit that I added in when I took the projective closure here, the complement of u inside y is a pentagon of lines, actually, an anti-canonical pentagon of lines. So this surface y is actually embedded anti-canonically in this projective space, and the hyperplane section at infinity is a pentagon of -1 curves. So if you know your del Pezzo surfaces, you'll know that a del Pezzo surface contains 10 -1 curves, or 10 lines. And so 5 of the lines have to live inside the surface U. At least all but one point of those lines lives in the surface U. And indeed, these turn out to just be the 5 straight lines, which are given by intersecting U with a coordinate hyperplane. And so we get this very pretty configuration, obviously very classically known on the left here. So on the left here, I get these are all of the 10 lines in the del Pezzo surface Y of degree 5. And each line meets 3 others. And there's a pentagon. The pentagon that lives at infinity to U is the thing around the outside here, D1 up to D5. And the other 5 lines, they meet in a kind of complementary pentagon or pentagram inside the surface U. So that's the complement. And so one way to see that you can get this as a blow up of 5 points is shown on the right here. So if I contract the lines E1, E2, D5, and D3, then I get this diagram on the right, and I can just blow those points back up to get to this picture on the left here. So the Pezzo surface is a blow up of 4 points in P2, as you see. Okay, so from this example, I just want to explain 3 things which we can generalize to the dimension 3 case in a nice way. So first of all, this surface U is a cluster variety, so I'll explain what that is in a minute. It's a cluster variety. I'll give you I'll explain what that is. Secondly, U, in a sense, it comes from the Grassmannian Gr25. So this is the Grassmannian that parametrizes 2 planes in a 5-dimensional space. I'll also explain how it comes from this as well. And lastly, this surface U, well, we can use it to construct a mirror for dp5. And again, I'll just give a brief explanation of what I mean by that in a second. But these are the 3 kind of things that I want to explain and then generalize to the dimension 3 case. So firstly, what does it mean to say that U is a cluster variety? Well, it's the interior of a log Calabi-Yau pair, YD. So here, Y is this smooth projective del Pezzo surface of degree 5. D was the pentagon of -1 curves. And because D is an anti-canonical divisor, when I add D to the canonical divisor of Y, it's trivial. So this is something that's called a log Calabi-Yau pair. And also Y is nice and smooth, and D just has nice simple normal crossings. So it's a very very reasonable pair to consider. And so what is a cluster variety? Well, a cluster variety is something that is the complement of an anti-canonical divisor like this. So it's Y minus D, where Y is a log Calabi-Yau pair, and we have this condition that that Y admits a toric model. So what does it mean to say that Y admits a toric model? Well, I have a map here. So pi is a map from Y to a toric variety, Y bar, and this is this Y bar D bar is a toric surface with its toric boundary, and this map is basically an isomorphism of D onto D bar. And so let me show you the picture. So on the right here, here's a picture. So if I have Y, I can contract two of the interior -1 curves. So these are called EIs. So if I take any two consecutive E1 and E2, for instance, they intersect consecutive boundary components. And if I blow down one of them and then the other, I get to this toric surface, which is the toric surface on the bottom on the left here, which has a pentagon in the boundary, but the self-intersection numbers on the edges of this pentagon are 0, 0, -1, -1, -1. So, of course, this is a toric variety because, for instance, if I blow down the -1 curve in the middle, I just get P1 cross P1. And so a cluster variety is the interior of Y, where Y has this map to a toric variety like this. And I can either contract, for example, E-1 and EI-1 and EI. I can contract two. I have to just, in order to get one of these toric models, I have to contract two interior -1 curves. And I can do that in 5 different ways. And the different ways that I can do this, the pairs that I can do this, they overlap with one, in this case, the two sets here, EI-1 and EI, they both have an EI in them. And if I change my point of view from blowing down E1 and E2, say, to blowing down E2 and E3, then I get a map induced between these two toric varieties on the bottom row here. And this is not a map of toric varieties. It's actually exactly induced by the Lyoness map, which is what we started with. So this two-dimensional Lyoness map is actually the kind of birational map that's induced between these two toric varieties. So you can think of it, and you should think of it, like an elementary transformation of ruled surfaces. So in this case, this map, what it does is it blows up a point in the interior of a boundary line, and so I get a reducible fiber. If I think of this as a ruled surface, I have a reducible fiber with two -1, -1 curves here in the middle, and I can blow down the opposite fiber of this in this fibration to get the next toric model, if you like. And so this kind of map here is called a mutation, and it's essentially exactly the Lyoness map that we started with. So that's what it means in this setting for this U to be a cluster variety. So it's covered by these 5. If I just look at the torus inside this toric variety, then that injects back into U because it lives inside U as the set of all points which aren't one of these two lines that we blew down in order to get to it. And the transition maps between these 5 torus charts is this Lyoness map. So I said there's also a relationship here with the Grassmannian Gr25. So the Grassmannian Gr25, where does that come into the picture? Well, I could write the equations of U. So there are 5 equations that define U, but U is a variety that lives in codimension 3. So it's not a complete intersection, but it is a Gorenstein. And for those of you that know, if you have a variety that's Gorenstein and in codimension 3 that's got 5 equations, then those 5 equations are probably coming from the Pfaffians of a matrix. So the Pfaffian of a skew symmetric matrix is essentially a choice of square root of the determinant. So what do I mean? So here I have a matrix, and I just have to look. I haven't drawn the zeros, and I haven't drawn the anti-symmetry. I've just drawn the strict upper triangular part here. So it looks like it's 4 by 4, but secretly it's 5 by 5. And I can delete one row and one column to be left with a 4 by 4 skew matrix. And I can take the Pfaffian of that to get an equation, and the 5 different ways of doing that give me the 5 equations that define this surface U. So if you know how to compute Pfaffians, you'll see instantly, and if you don't, then it's not a big issue, so don't worry. But I mean, I could homogenize. When I took the projective closure of this, I homogenized this matrix by just filling in all of the ones, making them linear of the same variable. So I could have put, you know, t's everywhere I see ones, and then that's the projective closure of this surface. But I could homogenize slightly more nicely, and if I choose this homogenization on the right here, where I've chosen 5, I've homogenized with respect to 5 different variables, and the 5 different variables, I call them y1, y2, y3, y4, y5. And I end up with this very nice homogeneous recurrence relation at the bottom here. So it's a recurrence relation in the xi's and these yi's. If you know what a frozen coefficient in a cluster algebra is, it's essentially that's what they are. And so instead of thinking of the original recurrence relation, which was just xi minus 1 times xi plus 1 is equal to xi plus 1, I could introduce these 5 variables, y1, yi minus 2, and yi plus 2, and I'd have this nice homogeneous recurrence relation here. And there's, of course, some kind of symmetry between the xi's and the yi's. It's not quite the same as swapping xi with yi. I think I have to swap xi with y of 2 times I. Or so here, I mean, xi is multiplied with its so xi, I mean, I multiply xi minus 1 with xi plus 1. Here I'm multiplying xi minus 2 with xi plus 2. At yi minus 2, yi plus 2. So there's a way to homogenize this recurrence relation nicely with respect to 5 parameters. That's basically the take-home message of this slide. And if I think about the affine variety that's defined by these 5 equations, now in 10 variables, it's very well known. It's just the affine cone over this Grassmannian GR25. So if you, I mean, essentially we can just take this to be the definition of the Grassmannian for this talk. It's just the variety that's defined by the Pfaffian 4 by 4 Pfaffians of a generic 5 by 5 skew matrix. And here is a very nice way to organize the variables in this matrix to get a nice 5 periodic recurrence relation. And something that's kind of interesting to do is if I take this new bigger affine variety U, which is now 7-dimensional, and I just look at the projection to the 5 variables that I've just added in, this gives me a fibration of affine del Pezzo surfaces. And so clearly, if I set all of the yi's equal to 1, then I just get back the surface that I started with, U. But in fact, the fibers of this fibration are all affine del Pezzo surfaces. I mean, this is flat, this map. And in fact, they're all isomorphic as long as I stay away from the coordinate hyperplanes inside A5. And if I do stray onto a coordinate hyperplane in A5, then the fiber starts to degenerate. And the very worst fibers in this fibration are the fiber over the origin, which is a cycle of 5 coordinate planes. So here in this very professional picture, I have U, which is the fiber over 1, 1, 1, 1, 1, and this cycle of 5 coordinate planes over the origin here, and this is kind of flat degeneration or toric degeneration of this U into this degenerate toric variety. And so this is the kind of, this essentially is the mirror family for the del Pezzo of degree 5 that appears in paper of Gross-Hacking and Kiel on Louis-Enger pairs, for instance. So I just throw this fibration out here because it's a useful thing to this is what we're going to look at in the dimension 3 case, and it's useful to mention it. And then very lastly, and also very briefly, this surface U can be used to construct a mirror, what's called a mirror for dp5. So what is that and how do I do it? So if I consider this invariant, I told you that the Lyoness map has d-1 independent invariant functions. So when d is equal to 2, then I basically only have one invariant function other than a constant map, and it's this function here, which is just the sum of all of the coordinates. So obviously, if I hit this by the Lyoness map, then it's 5. It just shuffles x1 to x2, x2 to x3, x3 to x4, and x4 to x5, and x5 back to x1. So W is an invariant. And there's a very nice way to write W, which is as a product of, this is what W is. The second line is explaining what W is as a Laurent polynomial in x1 and x2. So if I substitute x3, x4, and x5, what I know for them to be if I substitute the expressions that I know I have for those in terms of x1 and x2, then I get this thing on the second line. And I did the -3 at the end here because then that allows you to factorize the numerator very nicely, like I have done. And what I should do is consider a fibration. I can look at the map from U to A1, which is just given by this Laurent polynomial. So I just evaluate this Laurent polynomial at a point, just in terms of these coordinates. And because of this expression on the bottom row here, when W is equal to -3, or perhaps, when W is equal to -3, the fiber of this fibration has to degenerate because this polynomial here is reducible, and so the fiber splits up into several components. And actually, if you do this, go away and calculate, you'll find that the fiber -3 is exactly the interior pentagon E, and the fiber of infinity, which of course is not really part of this map, but that would be the divisor D if I were to extend it. And so if I want to extend this W, I mean, W is really, it's given by the pencil that of anti-canonical of elliptic curves that goes between E and D. So if I wanted to extend this map W to Y, I'd have a birational map to P1, where the fiber over infinity is D and the fiber over -3 is E. But of course, this map has has 5 base points, which is exactly the intersection of these two divisors, D and E. But if I blow these 5 points up, then I get an elliptic fibration that looks a bit like this. So it has exactly 4 singular fibers. It's a very well known example of an elliptic fibration with exactly 4 singular fibers. Over -3, I have the pentagon E, and over infinity, I have the pentagon D, and I have these 2 other nodal fibers that appear, and you have to do a calculation to work out where, but you can do that very explicitly. And so everything in this picture that wasn't contained in my original surface U is dashed. So that is the fiber at infinity and the 5 sections that I get here from resolving the base locus. And so thus the conclusion is that this fibration W from U to A1, well, this is a fibration of elliptic curves where each of the fibers has 5 points deleted. So this fibration of elliptic curves is supposed to be what's called the mirror of dp5. So it's a Landau-Ginzburg model. That means it's essentially a fibration of elliptic curves, or quasi-projective elliptic curves in this case. And the fact that there are 5 sections missing from this fibration, there are 5 points on every elliptic curve that have been deleted. These 5 points actually form they're the 5 torsion points of. So the fact that they've been deleted is something to do with the fact that this is supposed to be mirrored to a del Pezzo of degree 5 with an anti-canonical section, such that this anti-canonical section, the divisor zeros of this thing, is a pentagon of -1 curves. And so these 5 deleted sections are supposed to correspond to the fact that this S is a pentagon. It has 5 nodes, but it's not really very, let's not get into that. I mean, we just have this very nice fibration that's given to us from this invariant Laurent polynomial, which happens to be important for people interested in mirror symmetry. So now let me jump up to the next dimension. So this is hopefully the fun part, and explain how to generalize this into dimension 3. So if you recall from the beginning of the talks, in the 3-dimensional case, I have 8 functions. So this map is periodic of period 8, and I've only written out the first 5 here because it's probably not that helpful to just see complicated Laurent polynomials. So the question is now, what is the threefold that's defined by these 8s? If I had to take the ring x1 up to x8 and then quotient out by all of the ideal of relations that hold between these 8 things, then what threefold do I get, and does it have the same interesting properties that it had in dimension 2? And the answer to all of those questions is yes. So let me start by explaining how this is related to a homogeneous variety. So just as the affine del Pezzo surface in dimension 2, it turned out to be a kind of dehomogenization of the Grassmannian. So essentially this very special hyperplane section of the Grassmannian GR25, it turns out that in this case there's also a Grassmannian lurking in the background here, and that is the orthogonal Grassmannian. So actually in my title I had OGr 510, and it's traditional to talk about the orthogonal Grassmannian OGr 510, but actually it's completely equivalent. So OGr 510, first of all, what's the orthogonal Grassmannian? So the orthogonal Grassmannian parameterizes planes of a certain dimension inside a space of larger dimension, and these planes have to be isotropic with respect to a given quadratic form. And if the smaller number, so for example in the case 510, when the smaller number is half the dimension, this variety actually has 2 connected components, and those 2 connected components are isomorphic, and they're isomorphic to what you get if you subtract 1 from both those numbers. So OGr 510 is actually isomorphic to the orthogonal Grassmannian OGr 49, and I only switched to using OGr 49 because the explanation in terms of the combinatorics is slightly nicer from what I'm going to tell you. So let me just skip over this, because if you don't know about homogeneous varieties, it's probably not that helpful, but I'll give you a very explicit and concrete description of what this space is in a minute. But for those that know, the relevant Lie group that you use to construct this orthogonal Grassmannian is SO9, which is a Lie group of type B4, and it has a 16-dimensional spin representation. So this space here, which this group acts on, and this space is the given by the orbit of a highest weight vector in this representation. And so the weight polytope for this representation is actually a 4-dimensional hypercube in the weight lattice of this Lie group, and it has these vertices here. And the Weil group of this acts here as just the symmetry group of this hypercube, 4-dimensional hypercube, and the Coxeter element, which is the product of all of the elementary reflections. This actually acts as a rotation of this hypercube of order 8. So if that was mumbo jumbo to you, then hopefully the next slide will clear things up for you. If you want to define this space in a very concrete way, OGr 49, then this is the following subvariety of 16-dimensional vector space. So the 16 variables of this, well, this should be 15, P15, but it has 16 variables. So the 16 variables in this projective space sit on the corners of this hypercube. And let me label them y1 up to y8 and x1 up to x8. So this is a projection of a 4-dimensional hypercube. And it's a very nice projection. It's a projection onto the Coxeter plane of B4. And so you can see the 8-fold rotational symmetry, which is just the rotation of the Coxeter element that just rotates all of this picture around by 2 pi over 8. And this variety has a number of equations that come from faces in this hypercube. So every time for each of the 8 3-cube faces in this hypercube here, I can look at the 8 variables that live on the corners of this hypercube, and I basically have an equation that holds between the products of opposite corners in this cube. And there's a very nice way to write these equations. So I can write that here I have 2 kind of interior vertices which are projected to the interior of this cube when I take the projection, x1 and x4, and the product of those 2 things has to be equal to the sums of the products of all the things on the outside. So this kind of convention about signs is not the usual one that you take when you define the orthogonal Grassmannian, but it works, and it's related to something called the cube recurrence. And so I have 8 equations. I've drawn one of them graphically for you on the left here, and the other 8 I just get by rotating this picture. So I have x1 times x4 is sum of all these things, and if I rotate everything counterclockwise, I'd have x1 times x6 is a whole bunch of other stuff, and so on and so forth. So there are 8 equations I get by that, and there are actually a further 2 equations that are implied by those 8 equations, but also hold, and they come from decomposing this hypercube into bipartite vertices. And so if I decompose this cube into bipartite vertices, then I'm basically inscribing the 4-dimensional equivalent of an octahedron, and I also get 2 equations from this bipartite decomposition, which are like pairs of opposite vertices in an octahedron. Multiply those together and then add them in some way, and I get this equation x1 x5. So those vertices are actually opposite each other in the 4-dimensional octahedron. Minus x3 x7 plus x equals x1 x y1 y5 minus y3 y7. So this is a very nice algebraic variety. It lives. So just to summarize what happened on that last slide, here is a list of 10 equations with a very nice symmetry, and they come from this orthogonal Grassmannian in the way that I described. So really, for purposes of this talk, we can just say that this is the definition of this orthogonal Grassmannian. And now let me consider the affine cone over this variety. So that's just the affine variety in 16-dimensional space that's defined by these 10 equations with this very nice 8z over 8z symmetry. And if you notice, the first 8 equations that I've drawn here, they're a special homogenization of the 3-dimensional Lyoness map, Lyoness recurrence. So I have to add in the yi's, but I have to do it in this very special way in order to make everything play nicely. And then the last two equations, they're just two things that were kind of implied by the first 8. So they just pop out at the end. So if I had to set everything equal to 1 here, I would actually end up back with the threefold that's defined by the original Lyoness recurrence. And so, as I did with the del Pezzo surface, I can consider a fibration here. So if I consider the projection of U, this affine variety U, onto these 8 variables, so this is basically the y1 up to y8. These are the analog of the frozen variables in the previous case. Then instead of being a flat family of del Pezzos, this is now a flat family of affine Fano threefolds, and they're Fano threefolds of type V12. So a Fano threefold of type V12 is essentially an intersection of this orthogonal Grassmannian with 7 hyperplanes. And because this is essentially, so I'm taking 8 things here, but I'm also, U is the affine cone of the orthogonal Grassmannian. So really these things are, you can think of them as intersection of 7 hyperplanes in orthogonal Grassmannian. But the fibers of this map, however, they're not generic V12s. They're very special type of V12s, and the reason for that is if I were to take the projective closure of any one of them, I'd find that the boundary, the thing that I add in is V has to be very singular along that boundary divisor. So here's something that you can show about this fibration. So for any 2 complex numbers, lambda and mu, the fibers of this fibration are all isomorphic above intersection of these 2 quadrics in the base. So if I fix the value of y1, y5 divided by y3, y7, and y2, y6 divided by y4, y8, if I fix the value of those 2 things, then all of the fibers above that, all of the fibers of points with the same lambda and mu there have to be isomorphic. So you can just show that by hand. And so let me call a fiber that lives above this locus u lambda mu. And then for any lambda and any mu, which isn't 0, the projective closure of this affine Fano threefold of V12, it's a non-Q factorial Fano variety type V12. So the problem is, because these V12s, the central fiber of this fibration is very degenerate. So it's the cone over the picture that you see at the bottom here. So the bottom, I've drawn this, looks like a polytope. It's supposed to be 8 copies of P2 and 2 copies of P1 cross P1, which are the 2 squares glued in the obvious way. And so the central fiber of this fibration is the cone over this, is the 3-dimensional degenerate toric variety that's the cone over this surface. And because this divisor that I've added to this V12 is highly reducible, it must follow that the variety itself is singular, because this thing's generically they have Picard rank 1, but here of course the Picard rank is much bigger. I mean, there are 10 components in this divisor, so it has to have a lot of singularities, and you find that it has a lot of nodes. It has 16 nodes in the boundary here, which are basically at the points that I've indicated. And so in fact, if I consider the fibers of this fibration, they are all cluster varieties in the following sense. So I can project any one of them to affine 3 space and see what happens. And basically, whereas the del Pezzo surface was obtained by blowing up 2 points in the boundary of a toric variety, in this case, these threefolds, they're obtained by blowing up 3 centers in a toric variety, and you have to blow up 2 lines and a conic. So you can show all of this completely explicitly. So for a generic fiber of this fibration, if I look at the projection here to the affine space defined by the first three variables, then I'll find that it's an isomorphism away from the hyperplane, coordinate hyperplanes, and above the coordinate hyperplane where x1 equals 0, it contracts the divisor to a line. Above the hyperplane where x3 is 0, it contracts the divisor to a line. And above the hyperplane where x2 is 0, it contracts the divisor to a conic. And as long as lambda and mu are not equal to 1, these lines and conic are determined by the picture on the left at the bottom here. So this is just supposed to be a cartoon of what's happening. So the conic in the base has to touch the two lines, but the two lines generically don't touch in the x2 axis. However, some very special things can happen. So if one of these if one of these two parameters, mu or lambda, becomes equal to 1, then this configuration of things in the boundary here degenerates. So if mu equals 1, that's the easiest thing, then the conic that I blow up in splits into two lines, as we see at the base in the picture 2. And if lambda is equal to 1, then the two lines that previously didn't touch, they suddenly touch in the x-axis. And when I do this projection, P suddenly blows down a third divisor that gets contracted to an embedded point that lies in the intersection of these two lines. And if both lambda and mu equals 1, then both those things happen. So in this case, in case 1, this cluster variety is given by blowing up three things, two lines and a conic. In case 2, I have to blow up these 4 lines. In case 3, I have to blow up an embedded point, 2 lines and a conic. And in case 4, I have to blow up a point and 4 lines, as you see. And so if I consider the generic case where lambda and mu are not equal to 1, then I have 3 exceptional divisors for the projection. So the first of the 2 divisors, the first and the last, the ones that dominate the line, I can do a mutation, which is the change of toric model, which is given by blowing up L1 and contracting the divisor that is the strict transform of the divisor that passed through that line. And I can do that for each of these 3 centers. And so if I do it for E1 or E3, like I did for the del Pezzo surface, the mutation here is just essentially, it's just the Lyoness map that we started with, except that I have to homogenize the coordinates nicely, and I haven't applied the cyclic shift here, but that's basically what happens if I blow up L1 or L3. And you can show, if you take a picture like this, if you take a configuration like this and you blow up the line and contract the divisor that passed through that line, then you end up with a picture that looks exactly the same. And so so I get these are the mutation maps for E1 and E3. But what happens if I try and mutate the divisor in the middle here, the conic? Well, then I get this different mutation here, which is given by this expression. So the thing on in the numerator here, that equation, if I ignore all of the y's, it's of the form x1 x3 plus something times x1 plus something times x3 plus a constant, and so that is the equation that defines this conic that is the discriminant locus in the bottom plane. And so I have to mutate that, I have to adjoin this new cluster variable to my ring, which is just given by, this is the thing that I have to do. This is the mutation, algebraically, this is the mutation that I do to mutate at this conic in the base. And so this is a new variable. And although it looks very complicated, that to have a very simple description, which is that Q1 is just x1 times x5 minus y1 times y5. So, or equivalently, it's x3 times x7 minus y3 times y7. Because of that extra equation that we had, I have this coincidence that happens between these two things here. And so if I do that, and I also add in a Q2, which is the analogous thing but shifted around by 1, then and you work out what happens with all of these mutations, then you get a cluster variety. So the analog of a cluster variety, which has a very pretty exchange graph here. So essentially, I find 16 different torus charts or toric models that are related by mutations. And so the very top vertex of this picture here, where x1, x2, so there's a variable labeling every face in this polytope. At the very top vertex, the faces around that point are x1, x2, and x3. And if I go left, I mutate x3 to x8. If I go right, I mutate x1 to x4. And if I go down, I mutate x2 to q1 using this expression on the top line. And if you work out what happens, you find that all of these mutations give you this cluster variety with 16 charts, and they're related by mutations according to this diagram in a very nice way. And in fact, this also holds for all of the other cases when lambda or mu equals 1, even though there are more divisors to mutate in that case. So here's a proposition. So actually, in the worst case scenario, when lambda and mu are 1, then I have 5 divisors in the boundary, and I can mutate any one of them. So the fibers of this fibration, these affine Fano threefolds, they're cluster varieties, and their rank jumps as they become more degenerate. So the rank here is the number of divisors that I'm allowed to mutate at in any given seed. So generically, I have 3, but if one of the parameters becomes 1, I have 4, and if both of them become 1, I have 5. And you can calculate the number of different torus charts these cluster varieties have, and you can even draw their exchange graphs. And so here's a very, the exchange graph for the third case isn't so clear. It's a bit complicated, and a lot of the variables are squashed together, but a lot of the nodes are squashed one on top of the other. But at least you can see what happens. So on the left here, I have a 3-valent graph because I can mutate each model in 3 different ways, and this becomes 4-valent in the picture in the middle and 5-valent on the picture on the right. So these have very nice cluster-like structure. And let me just finally end with some words about mirror symmetry here. So if I concentrate on the very special fiber, the most degenerate one, for which the cluster variables that I have to add in to get this cluster structure are Q1 and Q2, so they have this form here, then if I just sum the x1 up to x8, and I sum these 2 variables that I have in this diagram that I had to add in to find the rest of the exchange graph, then this polynomial turns out to be a mirror Laurent polynomial to the Fano variety of V12, Fano threefold V12. So first of all, it has this very nice property that it factorizes when I subtract a constant from it, like in the Del Pezzo case. And so again, this implies the fact that this fibration here has a degenerate fiber when W is equal to -5. And so this Laurent polynomial, if you just go away and type it into your computer and you work out what the classical period of this thing is, you'll find that it agrees with the regularized quantum period of V12. So if you don't know what that means, then don't worry, but I know a lot of people listening will. And so you can use now the explicit equations of this cluster variety and the geometry that I've described, and I can write down a very explicit fibration. I can look at the base locus of this thing W when I take the projective completion, and basically doing exactly the same as in the 2-dimensional case, I can find what happens is you find this very nice and very symmetric pencil of K3 surfaces. So there's an involution, which is basically the involution that swaps the xi's and the yi's, exactly as in the two-dimensional case. There are two singular fibers, type 3. So these are degenerate K3 surfaces at -5 and infinity, and they are isomorphic and they're swapped by the involution. And there are also two other singular fibers in the sense that the Picard rank jumps at these 2 points. And so you get this very nice fibration of K3 surfaces by resolving this Laurent polynomial. And as in the dimension 2 case, I had to delete some sections from the elliptic fibration because they weren't part of the cluster variety. And what happens in this case is that I find that in order to resolve the fibration, I have to blow up in 24 different lines, and these 24 different lines are 24 minus 2 curves that sit inside the fibers of these of this fibration. And these 24 minus 2 curves, they have the dual intersection diagram here is drawn on the right. And these 24 curves actually span the Néron-Severi lattice of the fibers here. So the fiber is a K3 surface of rank 19, and these 24 curves sit inside that K3 surface and generate the Néron-Severi lattice. And as you expect, the orthogonal complement to that thing in H11 is just the lattice generated by an element of square 12, which is exactly the lattice that you expect to find because it's by mirror symmetry, it's the Néron-Severi lattice of a smooth K3 surface inside of V12. So it's kind of funny that I found a mirror to V12 inside V12, but as a kind of very singular thing. Sorry, I found a mirror to the V12, which sits inside an orthogonal Grassmannian, inside the orthogonal Grassmannian, but just as a very singular thing. And I don't think it just seems to be a bit of fun. And so let me just very briefly mention that the 8 terms you get from this recurrence plus the two new cluster variables, Q1 and Q2, you can use those just as building blocks to write down other interesting potentials on this variety U. So, for example, I could just, if I sum all of these things up, then I find I get a mirror Laurent polynomial to V12. But if I only sum some of them up, then I actually find I get other interesting potentials on this cluster variety, which give Landau-Ginzburg models, which are mirrored to different Fano threefolds. So actually, there's obviously 2 to the 10 different ways to add these things up, either with a coefficient of 0 or 1. And the 1,024 different possibilities actually only give very few period sequences if you compute the classical periods. And so there's only 46 different period sequences you can get from these polynomials, and 20 of them occur for smooth Fano threefolds. So, and there's a very nice little. So I've given 7 of them in the table there, but it goes down a bit further. And of course, there's a very nice little sequence at the start here that I wanted to just highlight, which is that if you just chip away from the right 1 step at a time, you find the sequence of Fano threefolds of index 1, but just starting from V12 and going up. And the fact that you have these different there's a relationship, the fact that I can think of these these polynomials all on the same space and the same coordinates, I can study the geometry. I can first of all, I can construct fibrations for other cases, and I can kind of, there's a kind of geometrical game you can play here where one of these fibrations degenerates into another one as you drop a variable in the potential. And so, for instance, here's how these are the extra -2 curves that I need to add into these K3 fibrations. On the left, there was the one for V12. and then becomes slightly more complicated further down you go. But I haven't really pushed this. I haven't really thought about this too much, but it seems like a lot of fun. So anyway, that was the end of the talk, and hope you could enjoy at least some of it. So sorry if it was a bit quick.